gentlemen, let's have another example. In this case, we've got a falling stone that falls by a window. Alright, let's read. A falling stone takes 0.28 seconds to travel past a window 2.2 meters tall. Question is, from what height above the top of the window was the stone dropped? You know what's going to help a lot with this? A diagram. Let's draw us a window. Alright. And just Wes at that time. Alright, so we've got our window. It's a little... Okay, so here's what we know about it. The stone takes 0.28 seconds to travel past this window. Right? So we have a time. Delta t is 0.28 seconds to travel this length. Okay? We know what that is. The window is 2.2 meters tall. So we're going to call this one delta y, because we don't know an initial y position, we don't know a final position. But we know if we subtract the 2, we get the change in position there. So that is going to be 2.2 meters. Now, there's something else we know about this, but they didn't tell us. So obviously, if the object is in free fall, right, it's operating under the influence of gravity. So its acceleration is, well, the magnitude of its acceleration is 9.80 meters per second squared. In this case, because the ball, or the stone, is dropped from up here and passes the window, and this is the only motion that we are concerned with, it's going to be a little bit easier to make downwards the positive y direction and upwards the negative y direction. In which case, the acceleration due to gravity, g, is going to be, well, downward in the positive y direction. So it's going to be positive 9.80 meters per second squared. Now, none of this yet really quite pertains to what we were asked. What we were asked for this was, from what height above the top of the window was the stone dropped? So the stone was brought up to this height and dropped by the window. So the question is, that delta y right there. Okay. Now, this one, we'll have to label them. I'm going to call this one delta y1, making this one delta y2. Obviously, the stone is going to travel through this length first before it goes through this length here. Now, we don't know anything else about this situation other than the stone was dropped. So one thing we could say is, at its initial position, its initial velocity is 0. Because we are labeling this as we like, let's call this initial position 0 also. So why not is 0 as well. So we're really just setting this up to take a look at what we can do with this. Now, just knowing these things really does not help us very much with this. We don't know a final velocity, we don't know a time, we don't know this distance. There's really nothing we can do with this information. And so what we're going to have to do in this problem and in many other problems is sort of split this up into two situations. Find how the two situations are connected to one another, and then solve one situation in order that we can solve for the next one. Well, obviously this one gives us nothing more here, so we're going to have to go to the situation where the rock is going past the window, just through this 2.2 meters. And we'll see that there is something that connects them here. Alright? We've already determined that this is y naught, right? And this is v naught for the object. Well, when it gets down to here, we can call this y1. And we can also call it v1. Because it'll have a new position, the top of the window, and a new velocity at this point, because it is accelerating. Which means that at the bottom here, this will be y2, and this will be v2. We don't know yet whether we'll need those values, but it is good to mark them off so that we know what they are. Or at least so that we can keep them in mind. Now, what we'll notice here is that if we're breaking this up into two situations, essentially above the window and along the window or past the window, those are our two situations, and there is something that they will both share in common. We'll see that the final position after it travels above the window here is the initial position for the travel past the window here. In an analogous way, the final velocity for this part of the motion could be deemed the initial velocity of this part of the motion. So either this value or this value will be the one that connects both of them together. Okay? Well, it turns out y1 is going to be very difficult to do that with. We just don't have a whole lot of information there. But we do have some information where we can find v1 here. Okay? So v1, we can use an equation that we've used before. Let's say y minus y naught plus v1 t is 1/2 gt squared. Now, in this case, y naught is actually y1, and y is y2. So y1 is our y naught, y2 is our y. And we'll see that we have enough information to solve for v in this case. Because even though I don't know these initial positions, if I just subtract 1 from both sides, right, I can see that y2 minus y1, well, that is just our definition of delta y, the displacement, which is something that we know. It is 2.2 meters in this case. So here we've got delta y is v1t plus 1/2 gt squared. We know what delta y is, we know what t is, and we know what g is. So this is just a matter of solving for the initial for this part of the motion as it goes past the window. In doing so, I'm going to subtract 1/2 gt squared from both sides. Leaving me with delta y minus 1/2 gt squared is equal to v1t. And in solving this for v, I'm going to divide both sides by t. So the velocity at that first position after it started its drop at the top of the window is going to be given by delta y, the height of the window, minus 1/2 g t squared, all divided by t. Now, because this becomes a rather lengthy algebraic problem, because I'm going to have to take this value and use it in the next one, I'm actually going to put some numbers in to solve for v1 at this point. Actually, I'm not going to do that. I already have it done. I'm just going to write it out at 6.485142857 Alright? So 6.48514, etc. meters per second. Now I'm doing this because this is not my final answer. I'm not going to round anything until the very end, alright? Until there is an answer that I'm going to report as the final answer, in this case, the height above the window that it starts from, then I'm not going to round a thing. I'm going to leave this in my calculator as it is so I can use it later. But let's take this back to our situation here and say that, well, we know what this velocity is now. It is 6.485 something. This is new information. I can now use this in this scenario here. When I look at this scenario here, now I can see y0 is 0, v0 is 0, and the final velocity is 6.485 meters per second. The acceleration is still 9.80 meters per second. I have a lot of information now and everything that I need to find delta y1 in this case. So I'm going to do just that, right? We're going to use this v1 squared equals v0 squared. It's 2g delta y. Sorry. Y minus y0. y1 minus y0. But you'll notice that's just a change in position from the point where it's dropped to the top of the window. Okay? We know it's dropped, so its initial velocity is 0. We know v1 squared because we just calculated that from the time it takes to go past the window. All we're doing is solving for y1 minus y0. We could even say that y0 is equal to 0. So in doing so, we're going to divide both sides by 2g. And we'll see we are left with just what we are looking for. y1 is equal to v1 squared over 2g. Now that we know v1 squared and we know g, we can simply put those in to get our value for y1 and how far down that is. Remember, I'm using the value that I got in my calculator, that 6.48514, etc. number for v1 at this point. Okay, when I do that, I'm going to get a value of 2.145769. Let's just round that up to like 2.1 meters. Okay. So now the big thing about this problem here, when you look at it at first, you're like, I don't know what's going on. Okay. And what we saw is that what we're going to have to do with this is split it up into two sections. And one section will inform the other. Okay? In this case, what we learned from the ball moving past the window informs the motion of the ball moving above the window. Alright? Yeah.